That's a light ray. By the way, if you're interested, when do you think of light as a wave? When do you think of it as a ray? It really has to do with what is interrupting the light. If that which interrupts the light is large compared to a wavelength, then it's more productive to think of light as a ray. If the object that interrupts light is comparable in size to a light wave, then it's more productive to look at light as a wave phenomenon. So right now we're going to start looking at sort of gross and macroscopic things. Imagine that we have an object here, which of course is interacting with the light. And if we stop and think about it, one of the interesting things about the whole physical world around us is most of the information we have about the physical world enters our bodies through our eyes. Did you know that 80% of the nervous energy in your body is used for your eyes? That's because eyes are the most important sense to humans. And so let's talk a little bit about this object interrupting the light in this room. The light in the room is spreading around and striking this object. And then that information of interrupted light is coming to my eye. Let's talk a little bit about that. In optics, we usually just draw the object instead of getting too fancy. The object is just an arrow like this. And the reason that we see that object is because light rays are diverging from that object, like this, in all directions. To use the proper term, we say it's an isotropic radiator. It radiates equally in all directions. And the way our brains and eyeballs work, what we do is we see a light ray, and our eye absorbs the light ray, and our brain extrapolates the light ray backwards to the object. So if I'm looking at the object, the fact that there's a light ray coming into my eye and being absorbed creates in my brain the ability to extrapolate backwards and say, oh, I see the object, it's over there. The light ray comes back from this other object. That's what's going on. We see things because of divergent light rays. Every point on an object is radiating. I chose the head of the object, but every single point is radiating. That's why we see all the points. Now, having said that, let's talk a little bit about what lenses do to light rays to understand those images that we were analyzing last week. And, you know, there's a preliminary experiment that I'm sure you've already done. It's an experiment that I think all young children like to do. What I mean by that is, I'm sure that at some point in your life you were probably wandering around in an old-fashioned stationery store where you found a magnifying glass. Usually a big lens like this with a chrome perimeter and a black handle. You pick it up and you run around and you play like Sherlock Holmes, right? Almost everybody's done that. And then I think you might have done something else. What you might have done is gone outside on a sunny day like today. The sun is up there shining away, and you take your lens, and the first thing you do is you kind of arrange your lens like this. The sun's up there and the lens is like that. And then you go looking around, you find your range, aha! And then you start looking for insects. Oh, there's a bug. Oh, there's another. I use sadistic pleasure. That's enough of an experiment to begin to understand lenses. Let's draw a picture of what's going on. First off, the sun, 150 million kilometers away, is shining, sending out light. Now these things that we always put on the sun, those are supposed to be divergent light rays. After traveling that far, 150 million kilometers, all divergent light will have diverged from the beam. In other words, by being so far away, all that means is all the light rays coming from the sun are parallel to each other. That's the most important thing. Now, the first thing I said that you did was sort of arrange your lens like this, and what I meant was you arranged it so that the face of your lens is perpendicular to the incoming light. So let me show that lens now in cross-section. Here's a cross-section of that lens arranged so that the axis of that lens is parallel to the incoming light beam, like this. The next thing I said you did was that you moved the lens in and out to find your range. That's the critical part of the experiment. Because what you've just discovered is that all the light rays that pass through the lens are bent in such a way that they all come to a focus at one particular spot like that. If I measure from the center of the lens to the point of focus, I will call that measurement F. That's the focal length of the lens. The point of focus is often called capital F. So there's the point of focus, that's the focal length. Now there's three interesting things I'd like to mention about this experiment. First thing you learn is that any light ray that strikes a lens parallel to the axis of the lens will be bent through the focal point. Let me say that again. Any light ray which arrives parallel to the axis of the lens will be bent so that it must pass through the point of focus, the focus point. That's principle number one. Oh, and by the way, just as physicists just hate to use a lot of syllables. So from now on, instead of saying light rays parallel to the axis of the lens, the term that we use is paraxial light ray. That means light rays parallel to the axis of the lens. So henceforth, I will use the term paraxial light ray. By the way, that means there is one light ray which is coming. Look, here's the, let's pretend like this is the axis of the lens, right, like this. There is one light ray coming right down the axis of the lens, and it continues straight to the point of focus. So a second interesting property about lenses is that any light ray going through the center of the lens goes through undisturbed. If you're wondering why, it's because the two surfaces of the lens right at the center, the two surfaces are parallel to each other like that. The center of the lens is just a window. It's the other surfaces which are sloped relative to each other that causes the bending. So we've now learned two things. That is, number one, paraxial light rays are forced to the point of focus. And second, light rays through the center of the lens go through undisturbed. The third thing is, and this is almost an argument until you do the experiment, this is almost an argument that you simply have to believe. And that is, it's called the principle of reversibility. That is, if a light ray passes through a lens following one particular path like this. So here this light ray is coming in paraxial and is bent through the focal point like that. If I was to turn that light ray around, it would back out of the lens along the same path. That is, this light ray, if I forced it to go through the focus like this and strike the lens, then it would leave the lens paraxial. It's called the principle of reversibility, that once you find the track of a light ray through a lens, you can simply turn it around and it will back out of the lens along exactly the same track. So those are three things that we can observe about light and lenses. And now we can use that to begin to understand the experiments that we were doing last week. What I'd like to do is to draw a picture, and what I'm about to do is called a ray tracing diagram. I'm going to do a ray tracing diagram. I want to draw a picture of a situation similar to the situation you were exploring last week. I do want to mention that when I use the term a ray tracing diagram, that means you need to be pretty accurate. In other words, you use very accurate measurement devices, you draw very straight lines, and you make careful measurements. That's a ray tracing diagram. A sketch is just a quick picture that you draw inaccurate. I'm going to do a ray tracing diagram. And to do that, I'm going to start by, what we typically do is we use various colors for doing ray tracing diagrams. And I like to use the convention that black is used for the lens. I don't bother to draw the shape of the lens. I just draw a vertical line to represent the lens itself. And then often we label it. In this case, I'm going to label it as a lens that has a focal length of plus 20 centimeters. So you label it like that. You draw the lens, you draw the axis of the lens exactly perpendicular to it, and then you measure out the foci. So at plus and minus 20 centimeters, I placed two foci, one on each side of the lens. So we do that in black. That's the color code. I'm going to emphasize the foci a little bit better now because I don't want to lose track of them. And then typically the last thing that we draw in black is the object of interest. So let me place the object of interest at some particular location now. Let me place it perhaps at 45 centimeters. So I'm going to place that thing about there. 45. And like I said, typically your object is drawn as nothing more than a vertical arrow to represent the object. So we have a relatively accurate picture right now of a lens, its axis, foci, and the object. Now, let's try to figure out where this thing is going to cast an image. Well, probably the best light ray to start with is the paraxial light ray. And let me use some other colors. I have blue. Okay, I'll use green. I'm going to use green for light rays, the color of light rays. Yeah. And probably the best way to start this thing is to start by drawing the paraxial light ray. So I'm going to do my very best to make sure this is paraxial. Let's see. So to get a paraxial light ray, I have to measure pretty carefully, draw this right from the head of the object right to the lens. And, remind me, what happens to that light ray after it goes through the lens? It has to go through the focus on the other side, doesn't it? So this light ray, I know for sure the destiny of this light ray, it continues on. Now let me choose, as a second light ray, let me choose this light ray. Look at this one here. This one is the one which goes through the focus on the first side of the lens. It goes through the focus and strikes the lens like that. So, oh yes, I know the destiny of this light ray. Please tell me what happens to this light ray. It leaves paraxial, doesn't it? It's the principle of reversibility, that's all. Now you know what, I better be very careful about this. So now, this one leaves parallel to the axis. If I've got any green ink left at all. And of course, now we understand why there is an image here. Because here are two light rays diverging from the head of the object. After those two light rays pass through the lens, they then diverge from this point. So if my eyeball is down here, like this, looking in this direction, I would see two divergent light rays, and they seem to be diverging from here. So my brain interprets that. I extrapolate the light rays backwards and say, well, if they're diverging from here, that means I'm seeing something here. So you see the image over here. Let's put the image in the same color as the light rays. So these two light rays, divergent from the head of the object, are also diverging from the head of the image. There are two real light rays divergent from the object and again divergent from this point. We call it the image. Now as a test, let's test our third light ray. Remember the third light ray? That was the one that goes through the center of the lens undisturbed. And, oh, I do have a blue pen. I'll use another color since green is running out. That says that there should be a light ray that goes through the center of the lens and continues through undisturbed like this. And lo and behold, it looks like that's true. As I put this blue light ray in here, this blue light ray is leaving the head of the object, it goes through the center of the lens, goes through undisturbed, and it does seem to be diverging from the head of the image. So this sketch seems to confirm our idea of that third light ray. Furthermore, those of you up close, maybe you guys at this table and that table as well, can see that it's not quite perfect. Why? Do you think the theory is wrong? No, you can't be very accurate with these kind of construction tools. You can imagine if I have very careful pencils and T-squares and very accurate 90-degree lines, that this divergent light ray would be much, much closer. This is off by probably a few millimeters. That's not bad when you use crude construction tools like this. So this ray tracing diagram seems to confirm our idea. What I'd like to do today, the first thing I'd like to do is each table, we want you guys to make a ray tracing diagram. And what I would like you to do is to, let's see, let's use a situation just like I have drawn here, except I'm going to make it a little bit different. And you know what? Let's say we're going to have a focal length, the object, black pen here it is. We're going to place the object at, let's say at x equals 5 centimeters. Let's place the lens at x equals, I'll put it in the middle, 50 centimeters. Let's say the focal length of the thing is going to be 15 centimeters, focal length, 15 centimeters. And I want you to find the position of the image. Okay, and I want you to do it with a ray tracing diagram. When I say that, when I say do it with a ray tracing diagram, that means absolutely no calculations whatsoever. Take your calculator, put it back in your backpack, you're not going to use it at all. You're going to draw a picture as accurate as possible to represent this configuration to find the x position of the image. Here is x equals 0. And so you're going to construct something like this using meter sticks and so on. To make it easy, at first your scale is going to be 1 to 1. Hence, therefore, you need a big piece of paper, don't you? So each table, we're going to go back and get a big piece of that butcher paper. Lay the butcher paper on the table. You would probably be wise to tape it down on the table. And then as a group, construct a ray tracing diagram. I would like you to use my convention, that is black, to represent the lens, the axis, the foci, and the object. Some other color to represent light rays. And find the position of that image, the x position of the image. That done, I'm going to create a slightly more complicated problem, a second problem for you, slightly more complicated. But each table, send back a representative, let's get some butcher paper and get this thing started. If it's got a cross-section like any one of these three, it's a positive lens, it's a converging lens. This one is called a doubly convex lens. This one is called a plano convex lens, and this one is a concave convex lens. Honestly, we don't really care what the specific shape is, you and I. We don't care. But any shape like that will give me a positive focal length. The next thing I'd like to talk about is negative focal length lenses. And they are either doubly concave lenses or concave plano-concave lens, or a concave convex lens, not really well drawn here. Those all give you negative focal length lenses. By just scanning those two sets of pictures, can anybody summarize a really easy way of determining the difference between a converging lens, positive focal length, or a diverging lens, negative focal length? What's the easy way to say the difference? I think he's saying it correctly if these old ears are hearing him accurately. That is, if it gets fatter in the middle, it's going to be a positive lens, a converging lens. If it gets thinner in the middle, it's going to be a diverging lens. All we care about, you and I, is what is the focal length. If it's a positive focal length lens, it's a converging lens, it has one of those three shapes. The diverging lens. Now let's talk a little bit about a diverging lens. Imagine that I have a lens whose focal length is perhaps 20 centimeters. So here's the lens, here's the axis, here's the object, and the first light ray that I want to talk about is the paraxial light ray striking the lens parallel to the axis. Then the difference is this light ray diverges as though it came from the focus on this side. Now the first tempting thing is people say, well then for the second light ray, why don't we take the light ray that goes through the focal length on this side? Does it leave there? No, we don't know what it does. On a diverging lens, at this moment, we do not know what it does. However, there is a second light ray whose destiny is known to us, and that is the light ray that does what? It goes through the center of the lens. Because even in diverging lenses, the center of the lens is always just a window. So there actually is a real light ray that does continue right through the center of the lens. Oh, and I just put it in black, didn't I? So now we have two divergent light rays which, when viewed from this side, look as though they were diverging from this point. Hence, therefore, we form an image here. But it's not the same kind of image. It's not like before. In the previous place, there actually were two light rays diverging from the location of the image. In this case, there aren't really two light rays which actually do diverge from this point. They look like they're diverging from this point, but they aren't. So this image is called a virtual image. It's not a real image, it's a virtual image. Why? Because there's not really two light rays there.
You can still see it.
From this side you can see it. But unlike the real image, remember the real image, we could put a screen and cast the real image? You can't cast this image. You can't put a screen there and have the image form as it does with a converging lens. By the way, now that you know that the image is there, now you can figure out this light ray. Because if this light ray was diverging from the head of the object, then after the lens, it should diverge as though it came from the head of the image. So now that I have found the image, I can do this. Look, I can put this here, that there. This light ray, now I know it diverges as though it had come from the image. So, I finally figured out what this light ray is going to do, but I figured that out later, after I actually found the image. So don't be fooled, just because we have paraxial diverging from the focal point. If it goes through the focal point, you don't know what's going on yet. After that, you don't know what's going on until you have actually found the image. Here is the image. And once you've found the image, then you can figure out any light ray that diverges from the object will be diverging as though it had come from the image on this side. If it's actually diverging from the object on this side, it will diverge as though it were coming from the image on this side. So once you've found the image, then you can figure out any other light ray you want. Just draw it from the object to the lens, and then away from the lens as though it were coming from here. That's all you have to do. Now, having said that, I would like you to get a clean piece of paper and reconstruct your experiment. Now, let me see if I remember your experiment correctly. I think you probably remember it better than I do, but I think what we have, no, I need it black for the axis. Let's see here. So here was the axis as though it were the optical bench. We had our object right at the end of the optical bench. And then I think at the 10 centimeter mark, x equals 10 centimeters, we placed the focal length of minus 150 millimeters. Is that correct? That's what I remember. Then you had some other position for the second lens. Let me just arbitrarily put it in somewhere else. Perhaps we'll put it at, oh, let's make it easy, x equals 50 centimeters. You can put it where your experiment found the second focal length. And that was 100 millimeters, wasn't it? It's really good to emphasize it when you're doing focal length. Just don't say there's an understood plus sign, put it there. And then you actually did cast a real image. The reason for that is because on this, between the two lenses, on this side, downstream of the negative focal length lens, the light is diverging as though it were coming from an image over here somewhere. So as far as this lens is concerned, it's dealing with light that seems to be coming from an image over here. So what you want to do is demonstrate that. First you find the image of the first lens, and you want to demonstrate that it acts like the object of the second lens by a ray tracing diagram. And that is, find this image, and then using a second color code, trace those light rays to find the second image, the image of the second lens. Okay? I think it's going to take another piece of paper, so we're grabbing a second piece of paper so that you're done with this problem and start setting up. I'm going to go up in the office and see if I can find some other colors of pens and pencils so that everybody has a good color code. I'll be back in a couple of minutes, hopefully with as soon as I find my
do this right there.
I can't see.
You already being lazy today so much.
That's my job.
Second picture we choose, sorry, the naked bubble, right?
No, the second picture's still out of the photo.
What? All right, thank you. 25 short.
Not 2 degrees. No, you
Where's the paper?
So it turn right.
Kind of
left.
What?
Right, left.
Wow, you did turn it with
That's useless to get in.
What are you talking about? It will go like that. I won't even use that part.
Sure.
We're not even going to use that quantity.
We're going to use it for a Molotov cocktail.
That doesn't make any sense.
It doesn't have to.
My phone screen is starting to die. It takes like several seconds for it to light up. So,
Wait, I got it.
It's probably too lazy to look up.
I really don't think that's the phone.
And from the circuitry, it is like.
What is this?
I don't think the phone has a look at it.
You'll just use one
There
side.
it does. It's time to take this. Sure, it depends on the manufacturer. Some bolts are lazier than others.
So we get you back.
Next one. Oh my gosh. So terrible.
it's an elder scroll.
It's just an embarrassment.
It is.
It's an embarrassment for me.
You want to go get another piece of paper?
Not really. I'm gonna just call it embarrassment, though. Just to pay them embarrassment.
No, the score has been missing.
Not that old.
It's so old, it's got battle screens. That's what the whole is. The top.
Where do you put these? I don't think
David needs to take this stuff down.
Hey, I get it.
Such a shield. Okay. Ah, too bad I put away the meter thing. Derek's the only one that has a messed up pizza.
We need to tape this though.
Oh, man.
Derek's the only one that has a
But thank you.
You're not welcome. Give that back.
Don't you have tape? Yours is all
Anymore. Thanks a lot. We could have been using it as a takeaway.
I guess so.
It's a pencil. It's all one up.
It's level relative to the stairs.
That's right.
That doesn't make any sense.
It does. It does. Everything is relative to itself. That's the reflexive property of geometry. Cool. No, it's true. 5 equals 5. So 5 was going to go at 5. Would it ever be relative? Exactly. Therefore, everything is relative.
Define 5 to be equal.
Yes.
Well, then 5 is the relative pair.
Well, no, then 4 is how do you do this?
Unless it's 5. Unless it's 5.
I resisted for so long.
I know, me too.
I used my very last.
Really? And you put it on stroke.
Oh yeah, you can.
Oh, dang, we get free tags. Also, these give us free games. The more added
Yeah, like that.
colors.
Visible to us.
Like green.
I have a green axis.
Ooh.
We have enough
Give it a
I'm
chance
not
anyways.
complaining. That wasn't it. Big bands.
So the reason I
I knew there was a reason I showed up that hour.
Let's take that up there. Okie dokie.
Okay, let's darken these axes. Make the axes more friggin' absolute.
So we're gonna go
Let's darken the axis.
10 centimeters.
Darken the axes first. We're going to any axis. It is straight enough. Okay.
Those lines.
Well, you did draw them. Space.
Yeah, just roll them up, okay. That's fine, I'll lay them flat out.
Get bent.
Hey, we're getting different.
Head run up that.
Dude, it's close enough. Whatever bentness you get is negative. Well, you put that under your assumptions.
Hold it good.
But it's class for an assumptions portion.
This is when the big one's gonna hit. You're like, oh, this crush it.
As long as they stay at each other, it's fine.
That's true. But if it ain't right, the engineering varies like this.
That second line sucked. Let me redo I'll tell you.
Google Sheets.
Are you trying to make it
Wow, let's look here. Yeah, why? Okay.
So 10 centimeters. I don't actually measure how far. I totally just fucked it up by now. Because we have two lenses, and we have to have an actual specific point away from the object.
This is awful.
You want to get us a new piece of paper?
No, you don't.
Okay, this is one of our lenses. There you go. This is a transparent lens.
You said.
This piece of paper.
No, you know you're just making it work.
I'll go get a new piece of paper. I'll get it from the piece of paper.
Yourself. Give us some favor. Scratch that.
I really hope he screws up on this. I don't think we're gonna use it.
I will. I will. What about you?
I did it straight at least, okay? No, this is legit. What? This is like.
Look at this divine piece of paper here. Divine.
Mine was divine.
Divine. Look at this. This straight and shit.
Hey, Jason. Don't throw that away.
I am. I'm going to throw it away right now.
Enjoy the right way.
It's too fucking thick. I can't even rip it apart.
It only has your money in it.
Don't hate.
Now I can solve
Relative to what?
Whoa.
That's what she said.
And I think you should lose your budgets. Well, we can start this month.
Yeah, exactly.
The other launch is
That's not very well.
No, it is.
I don't like Yanni.
Okay, let's try this again.
Okay.
Look.
The marker is there.
It's just getting a different piece of paper. That one's pretty.
This is a
It's not holding it down.
no, it's nice.
okay.
I heard that Roman love to use that.
Middle school, teachers like
Higher action, stronger.
Exactly. A paradox that will walk people forever. Actually, yeah, sort of hip hop. It's not a word. You can actually get this to work. Yeah. Why the fuck did you do that to my eyes? Exactly. See?
Say this is
See, it turns into words. So, action turns the head into words.
you're on to 10 centimeters.
No, our first.
I don't think so.
I didn't say it. Ask Professor Doyle.
Professor.
The ones that are from your back.
Okay,
Like you said, you're
So,
Just keep in mind, the whole thing you're trying to do is demonstrate.
I don't know if I have the experiment. I think I might have turned it with it. Oh, there it is. I have it with my experiment data. I don't actually have it recorded.
okay, so you have one at 110 and then one at 10. That's pretty far away. Well,
Are you sure?
the convex one was a 10. It was stationary at 10.
Okay.
And then there was the fourth one was using 50. So,
Why'd you say 110 first?
because that's where the original one was. That's for the first round. And then it was at 90 and then 70. Yeah, it just uses screw. We're just using our fifth one nowadays, so it's 10 and
I don't have the important one, but all the other ones.
we can use glue for the convex. Glue for the convex. And then black for the sounds like a cool story.
I know, but that's here. I'm missing